In this video, an important class of functions known as exponential functions will be introduced. An exponential function is any function whose rule takes the form f of x equals a to the power of x, where a is a positive constant number. Negative values of a are not allowed, since if we try to do calculations such as -4 to the 0.5 or -2 to the 0.1 on our calculator, you will find that you get a maths error. And that means that these numbers do not exist as numbers that we at the moment understand, which means that they're not real numbers. Now what we're going to do is we're going to have a look at the graph of a to the x, and to begin with we're going to have a look at the graph of a to the x where a is greater than 1. So let's have a look at the video. So at the moment we've got the graph of y equals 1 to the x, and now if we increase the value of a slowly, we can see that all of the time the curve goes through the point 0, 1. The curve is growing, and what we have here is known as an exponential growth curve. So if you've got y equals a to the x, where a is bigger than 1, we have an exponential growth curve passing through the point 0, 1. Now what we're going to do is we're going to have a look at the graph of y equals a to the x, where a lies between 0 and 1. And we've got a being 1 at the moment, and if we set the video going, then this time we can see again that the curve always goes through the point 0, 1, but this time we have got a decay curve. It's decreasing all of the time. Now let's consider the graph of y equals k a to the x, and we'll begin by considering cases where a is bigger than 1. So in this case we've got the graph of y equals 10 times 1.3 to the power x. We can see that the graph goes through the point 0, 10. And we can also see that we have an exponential growth graph. Similarly, if we look at the graph of y equals 3 times 2.1 to the power x, we can see that the graph crosses the y-axis at the point 0, 3, and that the graph is an exponential growth graph. So to generalize, we can say that if a is bigger than 1 and k is a positive number, then the graph of y equals k a to the power x is an exponential growth curve which crosses the y-axis at the point 0, k. Looking at this next graph, we've got the value of a is 0.85. We're looking at the graph of y equals 3 times by 0.85 to the power x. We can see that the graph is an exponential decay graph, and we can see that the graph is crossing the y-axis at the point 0, 30. And if we have the graph of y equals 50 times 0.37 to the power x, again we have an exponential decay graph, and the graph is crossing the y-axis at the point 0, 50. So to generalize these results, we've got if a lies between 0 and 1 and k is positive, then the graph of y equals ka to the power x is going to be an exponential decay curve which crosses the y-axis at the point 0k. We'll finish this video by having a look at this example. The table and diagram show the predicted value, v pounds, of a car at a time t months after the car is bought for £14,500. Looking at the scatter diagram in particular, we can see that we've got the sort of shape that we've been looking at in the previous slides, which suggests we might have an exponential decay graph relating the value of v to the value of t. Since the graph goes through the point 0, 14,500, it seems sensible for us to consider a rule of the form v equals 14,500 times a to the power t. But we clearly need to know what the value of a is. And we can get a possible value for a by considering one of the data points other than the first one. So in this case, I've decided to consider the data point when t equals 24. We know the value of the car is £9,500. So if we insert those values into our equation v equals 14,500 times a to the t, we've got 9,500 must equal 14,500 times a to the power 24. In other words, a to the power 24 has got to be 9,500 divided by 14,500, or approximately 0.6552. And if we take the 24th root of that, we've got a is 0.6552 to the 1/24th, in other words, the 24th root of 0.6552, which is 0.9825. So this is suggesting that we've got the rule as v is 14,500 times by 0.9825 to the power t. Now if we look at that rule and compare the values we obtain from the rule with the predicted values of v, we can see that they are pretty well in agreement. And if we look at the graph as well, the graph goes through the points, or very, very close to the points. So it does look as if the formula v equals 14,500 times by 0.9825 to the power t describes the value of the car after t months pretty well. So we can now say that after 20 months the predicted value of the car will be somewhere in the region of 14,500 times by 0.9825 to the power 20, which gives me £10,200. Similarly, after 25 years, which of course is 300 months, the predicted value will be 14,500 times by 0.9825 to the power 300, which gives us a value of approximately £73. The first of our two estimates is probably pretty reliable, because 20 months is well within the range of the observed values of time that we've been given inside the table. On the other hand, the value for 300 months, or 25 years, is well outside the range of values of t which we've been given in the table. And of course, a car which has survived 25 years might well either have been looked after very well, or might even have become a collector's item. So the value for 25 years is likely to be pretty unreliable. So the 20-month value is reliable because 20 months is well within the range of data values. The 25 years value is well outside the data values, so the prediction is unlikely to be reliable. And that ends our first look at exponential functions.